All right. Hello, people. I'm here in a lonely classroom talking to no one, but when you hear this, it will sound like I'm talking to you. So, hello, we are looking at our Concept 14 notes. So make sure that you have your Concept 14 notes out, ready to go. And we are going to look at two different things. We're going to look at our geometric sequences, which is all about like the bunnies that we talked about. And then we're also going to look at arithmetics. So the first thing we're going to do though is look at geometric. And yesterday you had, this is G, you did one that looks like this. And what happened was each time we were multiplying by 1/2. I know some of you prefer to say dividing by 2, but the reality is half of 12 is 6, and half of 6 is 3, and half of 24 is 12. So it is multiplying by 1/2. We did always have to find our initial value. And then what you see here, if I were to connect all of these dots, you see you've got this nice little curve going. This is called an exponential function, an exponential curve. And so you have never seen anything like that. They've always been quadratic or linear, things like that, or polynomial, crazy ones that we talked about last time, but never exponential. So this is a brand new idea that we are just beginning to touch on. So for the geometric sequences, the key thing is there is a common multiplier. So when you look at it, yesterday we had things like T of n is equal to, now I'm going to do something crazy, just crazy people. I'm going to write a whole bunch of stuff. This here, this says a sub 0. This means the initial value, or term 0. So it's not the first term. So if I have my nice little list here of my numbers, this is term 1, 2, 3, 4, but we went backwards and found term 0. In fact, let's put that example in there. We had 24, 12, 6, 3, 3 halves. So this is term 1, 2, 3, 4, 5. And then what we needed was term 0, so we found it, 48. So this is my initial value. So in this case here, T of n is equal to 48. R on the bunnies, hopefully you guys remember, that was our common multiplier. So we have fractions today, that's all right. So we have our common multiplier of 1/2. And then n, this dude here, that is our term number. So this is one way to look at it. The other way to look at it is we could have said a sub n is equal to 48, and then our common multiplier times n. So the nice thing is at least for me, when I'm looking at this, I'm like, well, I started with 48, and then I multiplied by 1/2, so it's 48 times 1/2. But I multiply by 1/2 over and over and over and over again, which is what makes it the nth power that I'm looking at there. Now, here's the kicker. If I plug in 4 into here, 48 times 1/2 to the 4th power. Now, that just means 1/2 times 1/2 times 1/2, 4 times. So I would do, what is 2 to the 4th power is 16. So this is really 48 times 1 over 16. And 16 goes into 48 3 times. So let's refresh. If I plug in 4, which is the term number, into here, I should get the 4th term. So today you're going to be finding some rules, and you can check them. You should check them. Don't say you can. You should check them by plugging in the term number into the rule and seeing if you actually generate it. You could plug in 2, you could plug in 3. I wouldn't plug in 1 because sometimes it works even when it's not supposed to for everything. So plug in 2 or beyond to make that happen. Okay, so that is all about on your common multiplier. And again, let's just make a quick little sketch of the picture. The picture was like this nice little curve. Oopsies. nice little curve going down like that. And we're just going to write exponential, because we are going to learn lots about that over the next several weeks. We're going to keep coming back to it until you get really good at it. Our last thing for exponential, if you wrote it like that, you would just have ab to the x. So again, it's just some initial value times some multiplier to the x power. So all of these things mean the same thing. These are all equivalent to each other. Okay, so we are now going to transition into arithmetic. So, did you get it? Did you get it? Did you get it? I hope you did. Arithmetic. And for the arithmetic, let's go ahead and look at a handy dandy little example. I'll box that just to be consistent since I did last time. We'll look at A. A is plus 3, plus 3, plus 3, plus 3, all over the place. So again, this is our first term, our second term, third term, fourth term, etc. And then I wanted you to go back and find the 0th term on each of these. And if you look at these, there's no curve here. In fact, if I just put a little, oh look, my stickers. If I put a little thing on here, this is line, 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 very, very linear in nature, which means everything you know, or are supposed to know about a line, is going to be true about this as well. A couple things I want you to notice. This is our y-intercept. Dude, that's our y-intercept. Our slope is up 3 over 1. Our slope is up 3 over 1. We have our change, our constant change is 3. And again, our 0th term is this one right here. So let's go ahead and see if we can jot down some notes here. So for these, since it was a common adder, we call it a common difference. And the common difference is just the difference in between them. So you could have a positive difference or a negative difference, and that would be fine. So the way that things that we know, let's just remember this is a linear, which is like y equals mx plus b. And so everything you know about that is also going to be true, but we're going to just kind of call them some different things here. We need to know this notation because we want to know things about the 4th term or the 5th term or things like that. So we need to have a way to kind of call that out. So we're going to write t of n equals a sub 0 plus d to the n. So what does that mean? This is my initial value, or my 0th term, or old school is the y-intercept, or b. This little dude right here is our common difference, or our change, or our slope, which is old school m. And then this guy here is our term number. So let's go ahead and put an example of A on here. So we had -1, oops, let me give myself some room. -1, 2, 5, 8, 11, which was our first term, second term, third term, fourth term, fifth term, and then you had to find the 0th term. So if we're adding 3, we do opposite to find the other one, which is -4. And so in terms of the rule, we would say that t of n is equal to, we start off with -4, and then we add 3. And we add 3, and add 3, and add 3, and add 3, and we just need to know how many 3's are we going to actually add. So this would be one way to look at it. You could also have a sub n. It's the same way of calling it out. So this is our y-intercept, this is our slope, or change, this is our common difference, and that is our term. So here's the deal. If you check it, so if I want to know my 3rd term, that means that if I do t of 3, so I'm finding my 3rd term, if I plug that in, I better get out 5, whoops, when I'm done. So this is what 9 minus 5, 9 minus 4 is totally 5. Check it. That really is getting me my answer. So please, especially today, you're not finding very many rules, When you do, go ahead and go back in and call it out and just check it to make sure that it actually does work. So the picture for this one was we started at -4 and we went up at what, -1 and 2 and 5 and 8. So this is very linear in nature. So that's what you need to know for today. Just make sure we're calling them the right things and finding the original ones. And good luck. Do awesome. I'll see you guys tomorrow.